about the only nice thing in Florida.
All right.
And the water, of course. Yeah.
So with rational functions, these are functions that can be written as the quotient of two other functions, p of x over q of x. Now what you really want to have here is that you want these guys to be polynomial functions. Okay? What was that about equal 0?
I said q can't equal 0.
Right, you don't, the thing here is that you can't have q of x, of course. It can't be what we call the zero polynomial. So it'd be a rational function, it's one polynomial divided by another one. But this bottom one can't always equal 0. Now, what we're going to see here is that we have vertical asymptote. So I'm just going to abbreviate this as VA. You have vertical asymptote when your denominator is equal to 0. You know how to find those restricted values, right? What are those values that make the denominator equal to 0? Those will become vertical asymptotes. How do you know about finding a y-intercept? What do you know about the y-intercept?
X equals 0.
Right. To find the y-intercept, just like we've always done, you evaluate f of 0. Does that sound right? Okay. What about your x-intercepts? Y is equal to 0, right? Now, you're right, Doug. We could set the whole expression equal to 0, but if you already have it as one fraction divided by another, you don't need to worry about setting the whole thing equal to 0. You just need to do this. You need to solve the equation where that numerator is equal to 0. For your whole expression to equal 0, it's going to be when your numerator is equal to 0. Okay. And of course, when we're doing this, I guess I need to tell you this.
What is VA?
Vertical asymptote, not Veterans Affairs.
Yeah,
I know. But what we need to make sure we have here with our function is that this guy is reduced. Okay. For you to find the x-intercept, you want that guy to be reduced, and you're going to solve that numerator equal to 0. Horizontal asymptotes are a little bit different, so we need to make a little chart here, give you some information. Horizontal versus oblique asymptotes. A horizontal asymptote is exactly what we've shown it to be, which is just going to be some horizontal line that you eventually start to get closer and closer and closer to on the edges, right? An oblique asymptote is pretty much the exact same thing, but an oblique asymptote, another way to say this is, sometimes you'll see it called a slant asymptote. It's a line that looks like this, and what you're going to see is that your graph will start to approach it as you get out here. It gets closer and closer to this line out in one direction, or the same way out in the other direction. It becomes closer and closer to that. And we're going to examine what that looks like and what it means in just a moment. But in order for us to figure out how we determine if it's horizontal or oblique, you have to know your degrees. Do you know how to determine the degree of a polynomial? It's the highest exponent, right? If you can do that, then we can do this. So let me just say this. If I say let m equal the degree of your numerator, p of x, and if I let n equal the degree of the denominator, q of x. To determine if you have oblique or horizontal asymptotes, you just have to compare degrees. That's it. Okay. And so let me show you the three different ways of figuring this out. Okay. So the first thing we have here is this. If the degree of the bottom is larger than that of the top, that means you have a horizontal asymptote of y equals 0. And I always like to think about it this way in terms of the string. By saying that the degree of the denominator is larger, I'm saying it's stronger. Okay. If the degree of your denominator is stronger, he starts to dominate on the outside. He's going to take over. It doesn't matter what that numerator is. Okay. So if the bottom takes over, that means as numbers get larger, the bottom takes over and he becomes larger. That means if your denominator gets larger and larger and larger, what does your number approach? It gets closer to 0, right? Okay. So if I had written this, if f of x is equal to x squared plus 3 over x cubed plus x minus 2, what's the degree of the top? The degree of the top
2.
is 2. What's the degree of the denominator? 3.
I thought it was 2.
You thought what was what?
I didn't think that was a plus, that looked like an x. X squared, x cubed.
Sorry, plus. So who's stronger? Who's more dominant, the top or the bottom? The denominator. Even if I wrote this, if I wrote 5x squared plus 3, who is eventually going to win this battle? 5x squared or x to the third? X to the third, because here's the thing about mathematics when we're talking about these asymptotes. We have all the time in the world as x goes out to infinity or negative infinity. So eventually, he will win. He will dominate, and he's in the denominator, so that will become a 0. Are you guys with me on that? Okay. If the degrees are the same, okay, then you will have a horizontal asymptote, and it'll be y equals a over b. And let me tell you what a and b are. A equals the lead. A is the lead coefficient of your numerator, p of x. And b equals, guess what? The lead coefficient of q of x. So basically it says if they had the same strength, if the top and the bottom had the same degree, they had the same strength, your horizontal asymptote is going to be the quotient of the lead coefficients. It will be the quotient of the lead coefficients. So if I were to say this, f of x is equal to 3x plus 7 over 2x minus 5, who's stronger, the top or the bottom? In terms of their degrees, their strength is exactly the same, right? Both to the first power. But this tells me that my horizontal asymptote, and remember these are equations of lines and you must give them as such. What do you think y is going to equal here based on what I just told you?
3/2.
It should be the quotient of their lead coefficient, so 3 over 2. As x gets really, really large, the 7 and the negative 5 start to matter less and less and less. So as these guys start to diminish and go away, you'd be left with an expression that looks kind of like this. And what does 3x over 2x reduce to? Doesn't it just reduce to 3 over 2? So we're not saying that we actually equal 3 over 2, but we're talking about what happens as we get further and further out. As x goes to infinity, we start to approach 3 over 2. This kind of goes back to that concept in calculus called the limit. You can't plug in infinity into this guy, but we could say this. So let me show you the connection that you'll see if you go on to take calculus. You'll see this. The limit as x approaches infinity of this function. Okay? So as x gets larger and larger, this guy gets larger, that gets larger, so it looks like infinity over infinity, which doesn't really make sense to us. However, what we've seen here, what we know, what we're learning about with rational functions, is that this limit is equal to 3/2. And if you don't believe me, you could go type this guy into your graphing calculator. So why not, right? So if I type in, make sure you use parentheses correctly, 3x plus 7 divided by 2x minus 5. If I go to my table, see what happens as x gets larger and larger. Is there a value that I'm starting to approach? Maybe. I don't think it will just let me type in a number. Nope. Let's change the table setup.
Oh, you can look for a number. Or is this table
If I change the table setup, so if I type in 20, I get 1.9. I type in 100, 1.57. Type in 1,000, 10,000.
Wow.
What's going to happen is it gets larger and larger. What is it approaching?
0.
Doesn't really look like it's approaching 0 to me.
Well, it's getting closer to 0, but yeah, I see what you're saying. Okay.
It's actually not getting closer to 0. It's getting closer to 1.5.
Oh,
So it says 1.5. If I plug in,
okay.
so I'm getting larger and larger here, and this guy's just approaching 1.5, right? A small little snapshot like this, you're saying, oh, this guy's approaching 0. However, you see that 1.5 really starts to stand out when I start plugging in larger and larger values.
So it'll stop at 1.5?
It will. Well, see, remember, you're dealing with limitations here with this calculator. So even though I typed in this, 100 million, it says 1.5. It's really 1.5, and there's so many zeros before it actually gets to something else that I can see that there's not enough room here for me to actually display that.
So is 1.5 the HA?
Yes,
Okay.
yes, exactly what I have here. 1.5 or
Oh, okay.
3 halves.
I see what you're saying. All right, there we go.
Because what happens is, if I plug in 1 million here and 1 million here, does the plus 7 or minus 5 really matter that much? So if I were talking about the ratio of how much money we earn, if I say I earn x plus 7 and you earn x minus 5, if x is 10, that's 17 to 5. That's a pretty big ratio, right? But if I say 100, 107 to 95, is that big of a difference? If I say a million, all right, I made $1,007 and you made $999,995. The spread there is very small, very insignificant at that point, right? So as these values get larger, these smaller guys right here start to mean less and less. But there's still some more situations for us to consider. We've talked about if the bottom is larger, it's dominant. If they both have the same degree, here's another situation. If the degree of the top is equal to the bottom one plus 1. Okay? So I'm not saying if they're the same, but I'm saying if the numerator is larger than the one at the bottom by 1 degree. Okay? That means we have an oblique asymptote that I'll abbreviate as OA. Okay? And you find it through long or synthetic division, depending on the setup that you have. You find it through long or synthetic division. For example, if I say that f of x is equal to x squared plus 4 over x minus 1. Notice how the degree of the top is larger than that of the bottom, right? How much bigger is it? By 1. So what I can do is that I can do synthetic or long division, and that will allow me to rewrite this guy. Okay. And let me show you what it means whenever I rewrite this. If I did this division just like you had on your last test, wouldn't you do the 1 out here? And then what would the coefficients be inside the synthetic division?
X squared plus 4.
What are the coefficients?
Oh, 1 and 4.
1, 0, 4. A lot of you
Oh,
left
right,
off the
right.
0 because I'm
Yeah.
missing that X term.
Yep.
So that's 1, that's 1, still 1, 1, and I get 5. Do y'all agree? Which means that this original function right here can be rewritten as what? If you had that problem of division on your test, when I do the division, I take these numbers, and what does it translate to be?
X plus 1 with a remainder of 5 over x minus 1.
X plus 1 plus 5 over what?
X minus 1.
X minus 1. Now I want you to think about what this means. We're talking about limits. I know it's a calculus concept, but that doesn't mean that we can't understand it or make sense of it now. As x gets really, really large, who becomes insignificant up here? As x gets really, really large, who starts to go away?
The constant. -1.
The constant's still going to be there, but what about this piece right here, this remainder piece? If x gets larger and larger, what does he start to approach? If I look at just this
Oh,
guy.
it's gonna be closer to 0.
This guy gets closer to 0, which means his pull, his power is weaker and weaker, right? So that means that if he gets weaker, he goes away, and that means my function starts to behave or look like this guy. And what does this guy look like?
Line.
It looks like a line, right? That means you have an oblique asymptote. So that if you were to graph this guy, that means you have x equals, or x plus 1 would give you a horizontal asymptote. That means the graph may do all kinds of weird things inside here, but as you approach on the outsides, you start to get closer to this guy like you've got to hug him. Okay, you know that's not anything that I would do. That sometimes mathematics will try to hug each other.
Do you hug?
I don't hug. Stop it. Now, looking at this guy, we've already talked about. I get a vertical asymptote from what? What makes this denominator equal to 0? 1. So if I'm here at 1, I also have this vertical asymptote. And so if you were to look at the graph of this guy, so I have x squared minus 4 divided by x minus 1. Nope. Did you see that? When it started graphing, it looked like it was just drawn.
So those dotted lines are your two asymptotes. One's the oblique, and then the other one is
Right.
the vertical. Okay.
Right, exactly. See, if I were to graph
I grabbed
x plus 1, if I graph x plus 1, I say that's my oblique asymptote. Watch how I graph. Watch what happens when I graph this. See how close it is right here?
Right.
Now it's not so close in the middle. I don't claim for it to be close in the middle. I claim for your horizontal and vertical asymptotes to be close on the edges. So as I keep graphing this guy, you see how he starts to become just like that guy again,
Oh, yeah, that's pretty cool.
right? So in the middle things get kind of weird, but on the outsides, you start to get closer and closer to this slant or oblique
So
asymptote.
technically, the two lines will never touch.
For this equation, they do not ever touch.
Yeah. Okay.
You can, like I said, it's like a horizontal
It's like
asymptote.
the
You can cross
1.5
it.
going out to infinite zeros with
Right.
1 on the end. Yeah.
Right.
Okay.
It's like a horizontal asymptote. You can cross it, but at the end, you're just going to get closer and closer to that. But for this particular example, they never cross.
Yeah.
I could have something that does this, but I got some kind of squiggle in the middle, and I go off and get closer to it again.
Why'd you graph x squared minus 4?
I graph x squared minus 4? That's a good question.
Yeah, it was supposed to
That should be a plus. Well, why didn't you guys tell me that? Now it's
I
for.
did, but
I
you
thought there was
were
nothing wrong with mine.
That's
you were
really
doing your own
different.
thing.
All right, so
Okay.
here's that guy.
How do you pause it?
You press the enter button to pause or unpause. Thanks for, making that video screwy now. I'm not going to re-record it.
I did say something, you just weren't paying
Yeah, whatever.
Two is like-
I don't want to hear this. I did this or you did that. He said, she said. They all said. Now, if that numerator is greater than the bottom one plus 1, then you have no horizontal or oblique asymptote. That means if I gave you this and I say f of x equals x to the third plus 2x minus 5 over 2x plus 3. Notice how that numerator has a degree larger than that of the denominator, but it's larger by more than 1, which tells me I don't have a horizontal or oblique asymptote. Because think about this, if you look at the dominating factors for this, the dominating factor for the top is x to the third, the dominating factor for the bottom is 2x. So the rest of the stuff is eventually going to become insignificant for each of the numerators and denominators. If you reduce x to the third over 2x, what does that give you? Something along the order of x squared, right? If you simplified x cubed over x, doesn't it give you x squared? So that tells you on the edges, you're not approaching anything that's a line. He's just going to start to behave more like a quadratic. And so quadratics don't have asymptotes. They don't have straight pieces to them.